Hi, this is a little demonstration having to do with tuning and temperament. And what I'm using here is this wonderful max patch called the Consonant Keyboard. And what this does, unlike the typical keyboard represented here, each of these notes is variable. So the exact pitch will change based on the calculation of the pure intervals. So if I push down this note and then push down the next note, it calculates a pure third using the Pythagorean ratios. So just to get into this real quickly, let's first look at thirds. So major thirds, you've probably heard this fact that three major thirds stacked on top of each other, if they are tuned pure, do not add up to an octave. Now on a regular piano keyboard, in a equally tuned, in equal temperament, the major thirds are larger, and so they do add up to an octave. But these pure thirds, you'll see very quickly and obviously, do not add up to an octave. Okay, let's just try that. There's one third, pure third, second one, a third one. I'm going to do this twice to make it more obvious. See where we are? Now if I lift that note up, we'll go back to the original pitch we started at. Practically a half step off. It's interesting. So it's a very clear demonstration of the fact that three pure thirds do not add up to an octave. Now I'll switch and do the same thing in equal temperament. So this is now playing in equal temperament. A little louder, I'm going to turn it down. No change. Those thirds sound in tune to us, I think most of us, but we're so used to those equal temperament thirds that they sound melodious to us, I guess. So the next thing is to take a look at how this device is working. So in order to get an idea of it, if you would focus your attention here on this display here. Now you notice, so if you would know from the harmonic series what the ratio of a major third is, you can figure that out using the harmonic series. If C is the fundamental, we go up an octave for the second. If we multiply that frequency times 2, we get an octave, times 3, octave and a fifth, times 4, 2 octaves, times 5, 2 octaves and a third. So the ratio between that third and the ratio between the fifth and the fourth overtone is 5 to 4, because they are 5 and 4 times, respectively, the frequency of the fundamental. So that's all to say that the ratio of the pure third is 5 to 4. Okay, so now if we observe, go back again, do the same thing over, and watch in the middle here what is happening with these calculations. So we see now it's multiplying it by 5/4. So the original frequency was 261, and that number times 5/4 is this one, 327. Okay, now I'm doing that same process again, multiplying that number by 5/4 to get 408.6. 1.79. Multiplying that number times 5/4 to get 510.98. Then I'm dividing it by 2 because I'm going down an octave. And I'm getting to 255. You can see that right here under frequency, if you can read that. And now if I release it, I see, oh, the original frequency is 261. That's middle C. Okay, so that's for major thirds. Let's think about this. We can also do this for fifths. Let's listen to what happens when we pile 12 fifths on top of each other, and see if we come back to C. Where we ended up. Let's lift it up and see where the C is. A little bit lower. It's rather subtle. Okay. So when we're stacking these thirds, you could say we're just sort of doing a calculation. We're taking this first frequency and multiplying it by 1.25, that is 5 to 4, same as 1.25, and doing that 3 times. And then we're asking, what's the result? Is it the same as 2? If it were the same as 2, this would be an octave, but we see it's not the same as an octave. So here in sound is this little bit of algebra. Which is basically saying that 1.25 times 1.25 times 1.25 equals 1.953125. That is, it does not equal 2. This is 1.953125, and here's 2. They're not the same. So this is all just reinforcing this point that the pure thirds are slightly smaller than the even-tempered thirds. As we see, one piece of evidence for this is that the 3 stacked pure thirds don't quite add up to an octave. So now we're just going to listen to some triads to see if we can sense the difference. So we'll start with equally tuned triads and just see how they sound with these. These are sine tone sounds that we're listening to. This is the equally tempered triad. That is the triad using equal temperament. Just intonation, or pure intonation. Can you hear how sometimes it's really hard to tell the difference. Can you hear how it's practically beatless, the pure one? Comparing equal temperament. can hear it sort of throbbing about this as wah, 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 wah. That one's throbbing about ya da 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 da. Faster, ya da 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 da. Okay, back to the pure, see if you can hear that. It is pretty subtle difference. It's sort of calm. There's just there are no beats. So let's take a look at a couple more intervals. The minor third, for instance. How does that compare to the equally tempered minor third? That is, what's the ratio? How does the pure minor third compare to the equally tempered minor third? Let's see. What the ratio of the minor third is, we can figure that out using the overtone series. I'm playing the notes of the overtone series. 1, 2, 3, 4, 5, 6. So the sixth partial and the fifth, the ratio from the note 6 times the fundamental to the note 5 times the fundamental is a minor third. So the minor third is 6 to 5. So let's pile them on top of each other and see what they do. See that if you look in the middle here, again it's calculating 6 fifths. We do that again. Bigger because it ends up being higher. We do it twice and see where we end up. So the original was quite a bit lower. That's for minor thirds. Let's think about major seconds. What's the ratio of a major second? I find this kind of enjoyable to figure out. So if we use the overtone series to get the ratio of the major second, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, the distance between 9 to 8. So the ratio of 9 to 8 is one possible overtone. One possible ratio for the major second. It also could be what? 8 to 7. You see in this program that when I push down the C and the D, I get a 9 and an 8. So if we pile pure seconds on top of each other that are the ratio of 9 to 8, let's see what we end up with. A little bit larger than the equally tempered major second.